Hello, and welcome to part one of our lecture this week on hypothesis testing. So we finished the exam. Good for you. Good job in getting it done and completed. I hope you did as well as you were hoping. I stated that at this point, after exam one, we're going to be getting into the different kinds of tests. So here we go. Today we're going to do a one sample Z test, which we've been familiar with up to this point. And from the weeks to follow, we'll be getting into T tests. But for now, one sample Z, we're familiar with it, but now let's get into the hypothesis testing of that. Excuse me. So here we go, hypothesis testing. So keep in mind that we're getting into the more inferential statistics part of the class now. So here's where we really start to kick it into high gear, or it's at least in statistical gear, So we use samples, just as a reminder, we use samples to infer information about the population that's too large for us to observe. So we can have a sample of 100, of 50, of 40, of whatever, and our population could be millions of people. So we use that sample of whatever, of 100, or again, 50, 40, whatever your sample size is, to make observations about what we think is true for the population. So as we talked about in terms of the sample means, when we select any sample from a population, it is obviously going to have a mean. You know, we have a mean of 25.2 for a sample of 40 in the population of college students or what have you. But on average, this will equal this sample mean that we've randomly selected will equal the population mean on average. That's the unbiased estimator. Now, selecting any sample mean from the distribution of sampling of this, selecting any sample mean from the sampling distribution of the means of the same population will be normally distributed. Now, this is the central limit theorem. Okay, cool, nifty, bitchin', we know this. Now let's get into hypothesis testing. So we use a sample mean to describe the population mean. So here is finally where we really get into using the sample to describe a population, inferential statistics, hypothesis testing. We can do hypothesis testing for everything moving forward. One sample Z tests, one sample T tests, independent sample T test, dependent samples T test, ANOVA. Hypothesis testing is with us every step of the way. There's 4 steps to it. I'll get into those. But we state the hypothesis regarding the value of the population mean. We select a sample and measure its mean. The larger the difference between the sample we have and the population mean that we're hypothesizing, the less likely that that value that we got for the population is correct. And finally, we use hypothesis testing in order to do exactly what it is that we're talking about, infer information about the population using a sample. Just like how this 4th bullet point is saying the less likely the hypothesized value for the population mean is correct, that is the information of the given population that we're trying to figure out. But I digress. So here we go. Let's kind of take an easy example. We'll work more with this later, but for now, let's just kind of see the steps. So first, the average consumer spends approximately 2 hours a day on social media. This is the population. It's just saying the average consumer. We're not really sure exactly who it's talking about, just, you know, the general public, essentially. We want to test if the premillennial generation, so the Generation Z, uses social media at the same rate as the average consumer. Okay, so now we have said, okay, we have a sample of Gen Z kids, and we want to compare their social media usage to the entire general consumer population usage. So that's not, you know, just, oh, another group. It's millennials, it's baby boomers, it's Generation X, it's everyone else that we're comparing Gen Z people to. Okay. So I mentioned how the hypothesis tests, how hypothesis testing uses steps. There's 4 of them, and we'll go into these in more detail as we go on, of course, as we use these steps. But here it is laid out. This is going to be the 4 steps we take for all of the tests that we cover from pretty much here on out. First, we're going to state the hypothesis or the hypotheses. We're going to set the criteria for a decision. So that's where we're going to have a level of significance. We're going to compute the test statistic. This part is going to change for every test we use. So z-tests, we're calculating the z-statistic as we're familiar with. T-tests, we're calculating a t-statistic, fancy that. ANOVA, we're calculating F, that comes out of nowhere, but it's fine. But different tests, that is step 3 of hypothesis testing, is where all of the different tests that we're going to cover in this class, that's where they start to stray at, or really start to stray at step 3. And finally, we're going to make a decision regarding our samples and our populations. So step 1, state the hypothesis. So we mentioned about the average consumer spending 120 minutes or 2 hours on social media per day. Well, let's keep it with 120 for minutes. So we start with the null hypothesis. So stating the hypothesis, we have to state a null and an alternative hypothesis. So let's start with the null. We always presume going into the test that the null is true. Okay, so the population of the average consumer, it mentioned they spend 120 minutes on social media. So that is our null hypothesis. The population mean equals 120. Now that H or 0 or H naught with the colon and then the mu equals 120, this is our null hypothesis. Simply stated, null hypothesis is the population mean is equal to 120. Okay. So when we do this test, we are going to determine if we will retain the idea or the notion that premillennials or Gen Z people spend 120 minutes on social media a day, just like the average consumer, or we'll reject that idea by saying that premillennials do not spend 120 minutes on social media. They spend more or less. So now the alternative hypothesis, essentially the null hypothesis, like I said, 120, that population mean that we have here, that's what we're thinking that premillennials are going with. We have a sample of premillennials and we know the population mean of the average consumer, but we don't know the population mean for just premillennials. So that's where this test is going. We're determining if premillennials spend more or less time than the average consumer. We want to know about the premillennial population. We already know about the average consumer population, hence 120. We want to know about the premillennials or Gen Z and see, okay, where's the difference? Is there a difference? That's what we have when we get into rejecting and retaining the null hypothesis. Excuse me. Now, the alternative hypothesis, I stated how in step 1 of hypothesis testing, I'm going to say hypothesis a lot, but in step 1 of hypothesis testing, we always come out of step 1 with a null and alternative hypothesis. So now we're getting into the alternative hypothesis. So this is H1 as indicated here. You can write it quickly as opposed to writing out alternative hypothesis. H1 is nice and easy. You can have different alternative hypotheses, and it really depends on the question. So we'll say there are 3 different kinds. There is that the population of the sample is less than the given population. So the population of millennials time, or excuse me, of Gen Z people's time on social media is less than 120, is greater than 120, or just not equal to 120. In order to determine which of those you're going to go with, less than, greater than, or not equal to, you need to read the question. You need to see exactly what it is they're saying. So let's get back to that really quickly. So we want to test if the premillennial generation uses social media at the same rate as the average consumer. So what we're looking for to determine if it's a greater than, less than, or not equal to alternative hypothesis is any sense of direction. So with that sentence, we want to test if Generation Z uses social media at the same rate as the average consumer. It's not really making any clear indication as to, we want to test if Generation Z uses social media more than the average consumer or less than the average consumer. It's just saying the same rate. So since we don't really have a clear direction as what we think that the Generation Z, their social media usage is, we're going to go with not equal to. So our alternative hypothesis is that the population mean for premillennial, or I keep saying premillennial like there's not a name for the generation, for God's sakes. So our alternative hypothesis is that Generation Z does not spend 120 minutes on social media. The population of Generation Z people does not spend 120 minutes on social media. Okay, so now that was step one. We walked out of step one with an alternative and a null hypothesis. Cool, bitchin', nifty, cool. Moving on. I already said cool. Anyway, cool squared. So now we're going to set the criteria for a decision. So in order to do that, we have to have a level of significance, which is considered to be a threshold we need to determine if we need to reject or retain our null hypothesis. Keep in mind that in this case, retaining the null hypothesis is saying that the population of Generation Z kids, people, retaining it, keeping the null hypothesis is saying that they spend the same amount of time on social media as the average consumer. And if we reject the null hypothesis, that's saying that the population of Generation Z people spends not the same amount. So they do not spend 120 minutes on social media. Excuse me. So typically our level of significance is set at 5% or 0.05. Keep in mind that this is similar to probability, where 5% is the same as 0.05. And when we talk about p-values, you can even think about that as a probability value, where the lower your p-value, the probability is, the less likely that you're going to obtain this sample from the population if it was 120. So let me kind of put that into more layman's terms. Essentially, our level of significance is set at 5% or 0.05. If we calculate this test and we have a p-value of 0.04, which is less than 5%, less than 0.05, we would reject the null hypothesis. We would say the probability that we would obtain this sample if the null hypothesis was true, if premillennials really did spend the same amount of time on social media as the average consumer, if Generation Z really did spend the same amount of time on social media as the average consumer, the probability of obtaining this sample mean that we got is 4%. And we have the threshold of 5%, so it's underneath the threshold, meaning, I don't really think that the 120 works for the population mean of Generation Z. I don't think it works for them. I think they have a different population mean that is not 120, that is not the same as the average consumer, that is not the that is not the null hypothesis. So we reject it. Anywho, so I mentioned how with alternative hypotheses, we have greater than, less than, and then not equal to. Well, in terms of what this means, and when we have a direction, meaning greater than or less than, when we're saying that we're anticipating our population to be greater or less than, the population of our sample to be greater than or less than the population of the general public or whatever it is, that is a one-tailed test. You can think of it like when you write greater than or less than, it's kind of like pointing. So it's one tail, I'm pointing this way, I'm only focusing in this direction. And then a two-tail test would be when we say it is not equal to. So what this means is when we graph it on a distribution, when we have a greater than, like this second one down here, the only area we're looking for to be significant is the shaded region right there. When it's a less than alternative hypothesis, the only area that would be significant is this area here, the shaded region yet again. For the less than, it'd be on the left of this little star. For a two-tailed test, you split the amount of probability for each tail. So you can see that it's actually, when you look at this, there's more area here than there is in one of the tails here for the two-tail, but it has to be split in half, so we still have an equal amount of significance on each side. We're just splitting it in half. So when we set our threshold, our level of significance to 0.05, the area of this shaded region here for one-tailed tests, either to the right for greater than or to the left for less than, the area of that probability, or of that part of the distribution, is 0.05. But when we have a two-tailed test, we split 0.05 in half. So we have 0.025 over here, half of 5, 2.5. And then we have 0.025 on the other side for a two-tailed test. This will come in handy. This will make more sense as we move forward. This is something that you'll need to know when we calculate one sample z-tests, which we're doing, because the problem with one-tail tests is that if you have an extreme value in the direction that you weren't anticipating, so let's say you have a greater than, you anticipate the population to be greater than, okay, so right here, the second one down. Well, if you have a super small population, or if your sample is way on the left here, it's not going to be considered significant because a one-tailed test is only saying the significant parts are here. But if it's like 15 standard deviations below the mean, like way over here, well, hot damn, that's pretty damn different. But since we only did a one-tailed test, it's not going to say that it's significant. It's not going to say there's a difference. It's going to say, nothing happened. It's the same. But that is why I do not like one-tailed tests, because you can be wrong. It's okay. We all are at one point in our lives. Well, probably more than one. But a two-tailed test is essentially saying, well, I'm not sure if this is going to be greater than or less than. I don't really want to make a decision either way. I want to give myself some wiggle room to see just kind of what the data tells me. I can't tell the data what to do. The data tells me what it's going to do. Anyway, so step 3, we got through step 1 and step 2. At this point, this is what we have. We have a null hypothesis of the population of Generation Z using social media for 120 minutes. My nose is itchy. Oh my God. Sorry about that. And then the alternative hypothesis states that the Generation Z people will not use social media at the same rate as the average consumer. So the null hypothesis does not, or the alternative hypothesis does not equal 120. Now we have our threshold of significance, our level of significance, also known as alpha, set at 0.05 or 5%. And since it's a two-tailed test, which we determined through the alternative hypothesis of not equal to, that's telling us that the each tail is going to have 0.25 area in order to determine the significance. Okay, cool. Now the test statistic. So this is essentially, it identifies how many standard deviations a sample is from the null hypothesis. It can be a negative, it can be a positive, at least for Z and T tests. And Z and T statistics, they can be positive or negative. We know that Z tests or Z statistics can be negative. For your homework, there was a negative 3.54. Oh, now I have the hiccups. Man, I'm just going through it right now. So you had a negative 3.54 Z. So we know that we can have negative Z scores. We also know we can have positive Z scores. And that's telling us how many standard deviations away from the mean that our score was. So now by having the test statistic, we can determine if we need to reject the null hypothesis, meaning that Generation Z does not spend the same amount of time on social media as the general population, or we retain the null hypothesis or keep it, in which we would say, yes, Generation Z does spend the same amount of time on social media as the general public, as the average consumer. Okay. So the larger the test statistic, the further the sample mean that we have strays from the null hypothesis mean. So the more standard deviations away from the mean that our sample is, the less likely that we're going to be retaining it, the less likely that the null hypothesis is going to still hold up to be true. We don't really say that the null hypothesis is true or false. Just for simplicity, I might mention that, but really when we move forward with statistics, with research methods, we tend not to say, oh, the null hypothesis is true or the null hypothesis is false. Anyway. So by calculating the test statistic, you can determine significance. You can also determine significance through the p-value, which I mentioned earlier. And this is, again, the probability of obtaining a sample if the null hypothesis was true. So the probability of getting the sample that we got, the sample mean that we obtained, if the null hypothesis is true. My nose is still itchy. Step 4. Make the decision, okay? You got two choices here. You can either reject the null hypothesis or retain the null hypothesis. So with rejecting it, this is saying that the obtained sample mean that we started with has a less than 5% chance, or 5% or less, of occurring if the null hypothesis was true. Since 5% is our threshold that we determined in step 2, our level of significance, if it's less than 5, reject. If it's greater than 5, we'll retain. Okay. And then I have a sticker on my foot. And then retaining the null hypothesis we do if our p-value is greater than 5%. Okay. So here's some tables and charts for your reference moving forward, kind of showing the difference between the population distribution, sample distribution, and sampling distribution of the means. So means for population is mu, variance for the population is sigma squared, standard deviation for the population is just sigma. Keep in mind that when we square the standard deviation, we have the variance, and when we take the square root of variance, we have the standard deviation. Ooh, humdinger. Okay, so now when we have a sample mean for the sample, so now we're moving on to sample. When we use the mean, we can use a capital M or an X bar, an X with a line across the top of it. Variance could be S squared or SD squared if you're so inclined. And standard deviation is S or SD. I mentioned that I will sometimes write standard deviation as SD, so that's why I also include that there. So now for the sampling distribution, the mean is displayed as this. So the mean of the sampling distributions on average equals the population mean. The variance is the variance of the sampling distribution is equal to the population variance divided by the sample size. And the standard deviation is, well, right there. Boom, bam. So the population, sample, and sampling distribution of the means. Here's more information. Again, it kind of tells you about these distributions, what it is it accessible? Can you see it? Can you have access to it? And what's the shape? So there we go. So, oh my God, errors in decision making. So when it comes to step 4, you know, we had two options. We either reject the null hypothesis or retain the null hypothesis. Well, there's a 50-50 chance that we can be wrong. So you have the decision to retain the null hypothesis is correct, so you did the right thing. The decision to retain the null hypothesis is incorrect, you didn't do the right thing. The decision to reject the null is correct, good job. The decision to reject the null is incorrect, you're bad. But it happens. This is common. It's so common that this happens that we have a name for it, type 1 and type 2 errors. So when you reject a true null hypothesis, you have a type 1 error. When you retain a false null hypothesis, I say the false and true thing to make it quicker. Oh my God. So when you mistakenly retain the null hypothesis when you shouldn't have, you have a type 2 error. Okay. So just to kind of show you a little visual, a type 1 error where you have a false positive, when you say that there's a difference, you know, I'm going to reject the null hypothesis, but it turns out the null hypothesis should not be rejected. You have a false positive. I have statistical significance, but you don't. So it's like telling a cis dude he is pregnant. All right. And finally, type 2 error is a false negative. So you're saying, nah, we got to retain the null hypothesis. There's nothing here. We do not have statistical significance. Retaining that would be like telling a clearly pregnant woman that they're not pregnant. Like, what? False negative. All right. So here's some information. I talked about how today we're going to be covering one sample z-tests. Well, one way to know that you're dealing with a one sample z-test is that it has one sample, so it's only mentioning one sample, and a standard deviation, excuse me, and it has a mean and standard deviation for a population. Z-tests will always have more information on the population in terms of if you see the population standard deviation or sigma, you know you're probably going to be dealing with a z-test. So let's take a look at this. An IQ test of a normal, healthy population has a mean of 100 and a standard deviation of 15. Okay, we collect a sample of 100 graduate students. So here we have our sample. You can also tell it's a sample because, well, one, it says we collected a sample, but it also gives you a number of people. Notice how when we say the normal healthy population with a mean of 100 and a standard deviation of 15, we're not saying any particular number. We're not saying, oh, the number of people in the population is such and such a thing. Typically, we don't have those numbers. So when you see, oh, we have a sample of 100 grad students, obviously it says sample, but when you have a number of how many there were, chances are you're dealing with a sample, but I digress. So we take a sample of 100 grad students to see if this sample of students is significantly different than the general population. So if it's different than the average normal healthy population with an average IQ score of 100 and a standard deviation of 15. So our sample of those 100 grad students had a mean of 103. Now let's determine whether we will retain or reject the null hypothesis when our alpha, or our significance level, is set at 0.05 or 5%. So that's a lot of information, but let's break it down. Let's break it down into the steps. So step 1, state the hypothesis. So it said that the average population score was 100. So our null hypothesis states that the population of graduate students, all the graduate students who've taken an IQ score, the null hypothesis is saying that theirs would be equal to the average healthy American, or I don't know, did it say American? No, just the average normal healthy population. Okay, so that's the null hypothesis, that the population average for IQ scores for grad students is the same as just the general population. Our alternative hypothesis, this is what has to contradict the null. So it's either going to be greater than, less than, or not equal to 100. So let's read the question. In order for us to know which direction, if it's greater than, less than, or not equal to, we have to read the problem itself to make that determination. So it says here, oh, we collect a sample of 100 grad students to see if this sample of students is significantly different than the general population. Well, it just says significantly different. It doesn't say significantly higher or lower, so we're going to go with a two-tailed test, meaning that our alternative hypothesis is not equal to the general population of 100. Okay, cool. So here's what we got so far. Null hypothesis, the average IQ score for the population of grad students will be 100. Alternative hypothesis, the population average for IQ scores for grad students will not equal 100. It will not be the same as the general population. All righty. Step 1, done. Step 2, setting the criteria. So we already know that our level of significance is set at 0.05 or 5%. Keep in mind that when we calculate p-value, this is in regards to p-value, this 0.05. If it's greater than that number, if it's greater than 0.05, we retain the null hypothesis. If it's less than 0.05, we reject the null hypothesis. Well, since we have a two-tailed test, we have to remember that our sample could be above or below the mean. So the distribution, wherever that our score would lie on the distribution, could be super high or super low on that Z distribution. We don't know. That's why we cut the alpha in half. So we can have a little bit of room over here. If it falls in this area of the distribution, it's going to be significant on this side. If it falls into this area of the distribution on this side, it's going to be significant. If this is equal to 0.025 on each side, this is a two-tailed test. I have my fingers on each side of the distribution tails. If it were a one-tailed test, instead of splitting it, they'd be together on one side or this side. So when we split it, it's still the same amount. It's just where are we putting it? Okay. So right now we got to deal with our test statistic. Now there's a way to determine significance through just the test statistic alone, and I will get into that. It's easier, it's quicker, but it doesn't tell you the exact probability like a p-value would, but it does let us know if we should reject or retain the null. But since we're doing a z-test, let's calculate the z statistic. Hey, fancy that. So in order to obtain our z statistic, we have to do our mean minus our population mean divided by the standard deviation of the sampling distribution. Cool. That's equal to the population standard deviation divided by the square root of our sample size. We do that, so our standard deviation of the population was 15, where it stated, oh, the average for the average American healthy, or it wasn't American, the average healthy person, their average was 100 and their standard deviation was 15. That's where we get this 15 from. And then for the 100, we had a sample of 100 graduate students. So that's where we get this. So we have 1.5. Now we plug that into the formula here. So we've done this already. Now we take 103, which was our, was our sample of grad students. So our sample had a sample mean of 103. So in case you're wondering where these numbers are coming from. So 103 minus the population mean of 100 divided by 1.5, our obtained z-score is 2. Okay, now we make a decision. Now we can determine significance just by looking at using that z-score by looking at this table. Keep in mind that this table only applies to z-tests, only z-tests. We'll get more into detail on that later when we cover the other tests, but this only deals with z-tests. So we can look at this chart and, okay, we have to know our level of significance, and we have to know if we have a one or two-tailed alternative hypothesis. So we know that our level of significance is 0.05, and we know that we had a two-tailed test, or not equal to, according to our alternative hypothesis, saying, hey, we're not really making any clear indication as to if we think that graduate students will have a higher or lower IQ average in regards to in comparison to the average population. So it's two-tailed. We don't know if it's greater or less than, so we just kind of kept it open. So we know that our critical values for our z statistic is going to be plus or minus 1.96. That's the critical value. Now what that means is that if our z-score is greater than 1.96, or if it's less than negative 1.96, then we can reject the null hypothesis. We have statistical significance. When we do not have statistical significance, we retain the null hypothesis. Those two things go hand in hand. So you reject the null, you have statistical significance. You retain the null, you do not. Mm-mm, 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 mm-mm. No, 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 no. Honey, I'm working, okay? All right, sit up here, but you gotta be quiet, okay? No, we're not playing. I love you. Okay, play with Chase, but you have to be quiet, okay? Okay. So we can, looking at that table, we already know that, hey, we're going to reject the null hypothesis. Our z-score of 2.00 is indeed greater than positive 1.96. Keep in mind, if your score is negative, you're going to compare it to the negative option. So if we had a z-score of negative 1.2, we would be comparing it to negative 1.96. And is it less than 1.96 or negative 1.96? Okay. So we had a z-score of 2. It is greater than our critical value of positive 1.96. So that's saying, hey, we have statistical significance. Keep in mind that z-scores represent how many standard deviations away from the null that we're looking at, how many standard deviations from the hypothesized null. So when we have 1.96 or negative 1.96, that's saying, hey, if your sample mean is more than 1.96 standard deviations above, or more than, or I guess less than 1.96 standard deviations below the population mean, you're going to reject the null. Okay, so we know that we're going to reject it with our z-score of 2, but we don't know the exact probability. That's why we use p-values if we're so inclined. The z-table that we've been using, that provides us p-values. That's probability. You know, up to this point, we've been saying like, oh, what's the probability of, you know, saying like between 45 and 80 times? We can use that z-table to indicate p-values. So we only, critical values serve as only, it tells you if you have statistical, Amelia, stop. It determines if you have statistical, Amelia, stop singing, stop. You have to be quiet, sweetie. If you want to play, you got to go to your room, honey. I asked you multiple times, you cannot, you can't be loud in here. You can't be playing around. Oh, Jesus, take the wheel. Okay, so if you have significance or not. So if you have, the critical values only tell you if you have statistical significance or not. They only tell you if you need to retain or reject the null hypothesis. It gets you in the club, in the significance club. Now, the z-table provides you the exact probability. So if we look at our z-table for 2.00, and we want to know beyond the tail, we want to look at column C, because that's where our significance is. That's where we want our values to be. So we look at the table and we have a p, or the value in column C is 0.0228. However, since we have a two-tailed test, this is not the p-value. The p-value, we actually have to multiply this by 2, since we split that p-value in the beginning to have 0.025 on one side and 0.025 on the other side. Well, now the value that we have in column C has to be doubled when we have a two-tailed test. So instead of it just being, oh my God, instead of it just being 0.228, we have to double that since we have a two-tailed test. So our p-value for this is 0.0456. Still significant, just like our critical value said, but now we know the exact probability. So here we go. I've already stated that we would reject the null hypothesis, but it seems like it takes us forever to finally get to step 4, that we forget what we're even doing. But we've rejected the null hypothesis, meaning that this is not right. The population of grad students does not have the same, the average IQ score for the population, I love you too, the average population for, the average IQ score for the population of grad students is not the same as the general population, the average healthy population. They do not have the same IQ score average. Okay, so let's do practice. A researcher is interested in knowing how often people talk about what they eat. The average person in the American population mentions their diet 14 times. So mu equals 14. I'm going to write this stuff down. You'll find that when you write this down as you're doing your homework or doing any practice problems or what have you, it's going to be helpful. So I know that mu is equal to 14 with a standard deviation of 6. Okay, so sigma or standard deviation equals 6. The researcher surveys 100 vegans. Ooh, that sounds like our population or our sample size. So n equals 100 to see if there is a difference between how often they mention their diet from the average American population. The mean for vegans, so our sample mean here, is equal to 15.5. Compute a one sample z-test, which we've been doing, to decide to retain or reject the null hypothesis. Oh, there's our level of significance right there. So alpha equals 0.05. Okay. Okay. So now let's get started. Step 1, null and alternative hypotheses. So the null hypothesis is saying it's just the same as whatever our population mean is. So the null hypothesis states that the population of vegans will mention their diet at the same number of times that the American population does. The alternative hypothesis is saying something different. Now keep in mind, we're either going to have greater than, less than, or not equal to when it comes to the alternative hypothesis. In this case, let's see. So the researcher surveys 100 vegans to see if there is a difference between how often they mention their diet from the American population. Well, doesn't say greater than, doesn't say less than, so I'm gonna say that it's not equal to. Oh my God, my freaking nose. Okay, so we have our alternative and null hypotheses. Null is saying it is equal to 14. Alternative is saying it does not equal 14. Okay. Step 2, setting the criteria for the decision. So we have our alpha set at 0.05. Now, we know that the p-value has to be less than 0.05 to be significant. Excuse me. Has to be less than 0.05 to be significant. Or if we want to use the critical values, we know we have a two-tailed test. We have a significance of 0.05. The critical values are plus and minus 1.96. Okay. So I've just written that right there. Okay. Step 3, calculating the test statistic. Now, lucky me, I also like to write the formulas down to keep them handy, because once I write down all the information from the problem, so I have my population mean, my population standard deviation, my sample size, my sample mean, I have all the information I need to fill out this equation. That's why I like to do that. Keep it easier on me. Okay, so we have to obtain our z-score, we have to do z equals, oh, well, before we start, it's the sample mean minus the population mean divided by the standard deviation of the sampling distribution of the means. But in order to get the sampling distribution of the mean standard deviation, we need to take the population standard deviation and divide by the square root of the sample size. So let's start with that. That's what we did last time. We started with finding the standard deviation of the sampling distribution of the means. So let's do that again. That is what we have to do first anyway, because in order to actually do this equation, in order to get z, this, we gotta do this, which is, you know, over here. Okay, so let's plug it in. So our standard deviation for the population is 6. divided by the square root of the sample size, which is our sample size is equal to 100. So 6 divided by the square root of 100, that is 0.6. Yes, Amelia. So we have 0.6 so far. 6 divided by the square root of 100. Again, this is what I just did. This part right there, or that whole thing, not just the square root of n. But that's what I've done so far. Now I can plug in the number I just calculated into the equation for z, since I've gotten that bottom part down. So the sample mean, so 15.5 minus the population mean of 14 divided by the standard deviation of the sampling distribution of the means, that was equal to 0.6. Oh wait, hold on. That's what I got so far. Now it's just an easy calculation. Let me just get my handy dandy calculator. So 15.5 minus 14 is 1.5 divided by 0.6. Our z is equal to 2.5. Now I can look at the critical values, plus minus 1.96. And since our z is greater than the positive critical value of 1.96, I can say, hey, we reject the null hypothesis. That's cool, but let's get the p-value first. Or, well, let's get the p-value as well, I should say. So, oh, wait, hold on. Okay, so here we are, the p-value, or well, the z-table. Back at it again. So let's find 2.50. And we're looking in column C. So here we go. Column C, we got 0.0062. But since this is a two-tailed test, that is not our p-value. We have to multiply that by 2 in order to get our p-value for this one sample z-test, which was a two-tailed test. Okay, so 0.0062 times 2, our p-value is 0.0124, or you can just round that to 0.01. Okay, so our p-value equals 0.01, which is indeed less than our threshold of 0.05. Here, let's go back to the PowerPoint now. Okay, why did it do that? Okay, there we go, sorry about that. So this value of 0.0062 is what I found in the z-table. Since we have a two-tailed test, we multiplied that value by 2 to get our p-value. So let's make a decision. Should we reject or retain the null hypothesis? Well, our z was greater than our critical value. Our p-value was less than alpha, so our p-value was less than the level of significance. It seems backwards because, oh, our test statistic is greater than the critical value. That means we reject. And our p-value is less than the level of significance, so we reject that as well. So it's kind of opposite. It's weird. We'll get into more detail about that at a later time, but that is how it is. So I'll also include a table to help you guys keep it straight, to like what it means when you reject the null hypothesis, what it means when you retain it, just to kind of, keep your mind at ease. Okay, so I've mentioned it several times already, but with this case, we would reject the null. So this is saying that the population of vegans do not mention their diet at the same level of times that the American population does. So vegan population does not mention their diet at the same rate I'm running out of room as the American population. I'm going to show you what I wrote, which is exactly what I just said out loud. So in case it was hard for you to read that, what I wrote was I rejected the null hypothesis. I abbreviated it to H naught just because, you know, I was afraid I would run out of room. But the vegan population does not mention their diet at the same rate as the American population. That's what that said. Okay. So that is our introduction to hypothesis testing, the 4 steps involved, and just, you know, what's involved in that. So we're going to follow that series of steps with all the different tests that we do. This was a one sample Z test. Next week, we're going to be covering 1 sample T tests. We're going to get into independent samples, T test, dependent samples, T test, la-di-da-di-da. But when you see Z as the test statistic, we're dealing with the Z test. And in this case, it is called a 1 sample Z test. But that is all for today, or at least for this lecture. I hope you found this helpful. If you have any questions, don't hesitate to send me an email or stop by my office hours. You know, I'm happy to help you through any of this, explaining it, kind of clearing up your mind if you're kind of confused. But that's all I got for you. So enjoy it and like and subscribe.